Hi everyone. So we're going to start by looking here at Earth's atmospheric layers. Sorry, not labels, layers. And I wanted to keep this. We're going to show a video. I want to keep this little diagram open, and I'm going to explain the diagram a little bit before I show you the video. I'm going to keep it open at the same time as we watch the video, so we will not have it in full screen. Okay, so if you take a look at this diagram, this shows you on this axis the altitude in kilometers, okay, and then the different layers of the atmosphere that we're going to study. So we have the troposphere, the stratosphere, the mesosphere, and the ionosphere. People often split the ionosphere into several other layers. So in the video, you'll see that they split that. On this axis, we'd see the density, right? So the density is, of course, higher at the bottom, right, in the troposphere. And on this axis here is temperature, and this orange line shows you the temperature changes for each of these layers, and it's a weird jagged line. So if you see here, in the troposphere, from the bottom to the top of the troposphere, we see a decrease in temperature. Notice that if we go this way, the temperature is decreasing, as you might expect, right? Higher elevations are colder. Now, as we go to the stratosphere, which contains ozone, we see that we get a temperature rise, and we're going to explain that in the video. And then in the mesosphere, another temperature drop, and then in the ionosphere, a rise in the temperature. Okay, so let's take a look at the video and keep in mind this little plot as we watch.
Layers of Earth's atmosphere. The 5 main layers of the atmosphere are divided according to their temperatures. The lowest layer, the troposphere, varies in height around Earth depending on the warmth of its air. Troposphere is the thick, heavy, moist layer closest to the Earth's surface. Warmest at ground level, it cools with an altitude to as low as -70 degrees centigrade. It is about 16 kilometers high at the warm equator, but only 9 kilometers high at the chilly poles. The stratosphere has most of the ozone layer, which absorbs almost all of the sun's harmful ultraviolet light. Because of this, the air warms up to 4 degrees centigrade. The mesosphere, the coldest layer, does not absorb much of the sun's heat or ultraviolet light, so its temperature can drop to -90 degrees centigrade. The air here is thick enough to slow down and burn up meteorites. The exosphere, where Earth's atmosphere fades into space, contains hardly any air, but its temperature can reach up to 1650 degrees centigrade. In this region, the air is so thin, a person or spacecraft would not feel the heat. The air in the thermosphere is very thin, but it is thick enough to absorb the sun's ultraviolet light. This light, which is invisible to human eye, heats the thermosphere up to 1480 degrees centigrade.
Okay, so let's unpack that a little bit. All right, let me get the slideshow going here. All right, so come on, slideshow. There we go. Okay, so if we look at, like in the video said, right, we have this layer of ozone in the stratosphere that is very protective of us from ultraviolet rays from the sun, and it also is sort of trapping heat. Now, you might have heard of holes in the ozone, right? This happens because of pollutants like fluorocarbons that are put into, say, a spray can, right? And in the 70s was sort of the heyday of those spray cans, and then people, whenever you used hairspray, there was a fluorocarbon that was used as to make the spray come out, basically. And that was causing holes in the ozone. And ozone is basically a region where you have a particular molecule which is 3 oxygen atoms together and form, forming a molecule with 3 oxygen atoms. So that's ozone, and that is just very protective when we want to keep that. So we don't want holes in the ozone. So there was a lot of laws passed about not having those in the in consumer products, let's say. Okay, so very important to keep that ozone, and you can see that it's sort of trapping the heat, which is a good thing. We're going to talk about greenhouse effect in a little bit, and of course that's related to global warming. But of course you do want to keep the heat in a bit, as we'll see in the next video. Okay, so let's talk a little bit about the ionosphere. So the ionosphere is that lower part. He didn't really talk about that in the video, but you could see with the how far up, right, the exosphere and the thermosphere were. He was going much farther up than this diagram does, right? And saying that the exosphere, which is kind of the interface with space, right, and which is the highest level of the ionosphere, can get very, very, very hot. Well, I hope you remember that if something is hot, that means the molecules are moving very fast. But if you have very few molecules, you're not going to feel the heat. Okay. Let me give you an example. So if you think about a pot of boiling water, there's a lot of molecules very close in the water, very close together. Those water molecules are really close together, slipping over each other in a liquid. And let's say it's 100 degrees. Well, that's Celsius, so 212 degrees Fahrenheit. It's boiling. Now, if you put your hand in there, you're going to get very severely burned because there's a lot of molecules to hit your hand and impart their energy to your hand, and therefore damage your hand, right? But think about turning your oven on to 212 degrees, which is a pretty darn low oven temperature, right? You might be slow roasting something in there at that temperature. But you can stick your hand in that oven. Once it comes up to temperature, I turn preheat on. You can stick your hand in that oven, and yeah, it feels hot, but you're not going to burn yourself, right? Because you're sticking your hand into hot air, which is a whole lot less molecules, right, than per, let's say, square meter, right, than the water molecules. Those are very closely packed. So it's the same idea when you go up high, high, high in the atmosphere. You have very, very high temperatures, which means the molecules are going very fast. They've been heated up by the sun, but you wouldn't feel it because there's so few of them, okay? Anyway, interesting. So let's move on and talk about the greenhouse effect. And I'm going to show you a video first, and we'll just sort of unpack that a little bit. So let me go back to, oops, that's not what we wanted. Hello. Yeah, my computer's yelling at me. Go back to our video here. Here we go.
How do we know that greenhouse gases lead to warming? As early as the 1820s, scientists began to appreciate the importance of certain gases in regulating the temperature of Earth. Greenhouse gases, which include water vapor, carbon dioxide, methane, and nitrous oxide, act like a blanket covering the Earth, trapping heat in the lower atmosphere, known as the troposphere. Although greenhouse gases are only a tiny fraction of Earth's atmosphere, they are critical for keeping the planet warm enough to support life as we know it. Here's how the greenhouse effect works. As the sun's energy hits Earth, some of it is reflected back to space, but most of it is absorbed by land and oceans. This absorbed energy is then radiated upward from the surface of Earth in the form of heat. In the absence of greenhouse gases, this heat would simply escape to space, and the planet's average surface temperature would be well below freezing. But greenhouse gases absorb and redirect some of this energy downward, keeping heat near the surface of Earth. As concentrations of heat-trapping greenhouse gases increase in the atmosphere, Earth's natural greenhouse effect is amplified, like having a thicker blanket, and surface temperatures slowly rise. Reducing the levels of greenhouse gases in the atmosphere would cause a decrease in surface temperature.
Okay, so that's, the cause of global warming, right? Too many of these greenhouse gases in the atmosphere. Let's talk a little bit more in depth. Well, we're not going to go too much in depth into this whole greenhouse effect. We will talk a little bit more about that when we talk about Venus, because Venus has what we call a runaway greenhouse effect. Very, very hot temperatures on the surface of Venus, but we'll get there later. So a lot of the sun's solar energy makes it to the Earth's surface, so it goes right through the atmosphere, and the greenhouse gas is what traps that heat. Now, like the video said, we would not be here if it weren't for those greenhouse gases, right? So we're lucky we have some, but what the problem is that we pump more and more of these greenhouse gases into the atmosphere from burning fossil fuels, say, right? Then we are going to, put on a thicker blanket, like the video said, on the Earth, and this is what is causing the rise in temperatures that we see in the next plot. I should probably start the slideshow if I can get my computer to behave. Okay, there we go. Come on, there we are. So here you see a plot that goes from 1400, right, to the year 2000, and you can see the blue line is the departures, right, from the average. All right, now what does that even mean? So if you have, an average, sort of a moving average, then you can say, hey, how different is the temperature today than the average over a certain period, right? That's what's shown on this graph. And you can see as we approach 2000, there is a very large departure from what has been the norm for a very long time. And you can kind of see that, this is coinciding with the industrialization of civilization, right? So not just the Industrial Revolution, which was starting around 1800, but the sort of massive industrialization of our society. And again, I hope that you know that this is not a class on climate science, but I hope you know that this is a very well documented and tested idea and measured idea that we are causing this climate change, and it's going to be a big part of our lives, and hopefully not a destructive part of our lives, unless we do something about it. Okay. All right, so let's switch gears here, and we're going to talk a little bit about the magnetic field that protects us. So Earth actually has a magnetic field that is surrounding it. You probably know that because as a kid you probably played with a compass, and little needle that's suspended on a little point, and it turns and points your direction towards north. That is just a little magnet in that compass. That little needle's a little magnet, and magnets line up along magnetic fields. And so that's how a compass works. And if you see, we have kind of these magnetic field lines coming out. This basically is the same shape of field lines as you would have from a fridge magnet. So if you have one of those fridge magnets, they're holding up papers or pictures on your fridge. If it's kind of a little bar, right? Then your field lines will look very much like this. These kind of big curly lines, and they're protecting us from charged particles from the sun, because those are not good for us. So we do not want to be bombarded by charged particles. That would give us cancer and probably would have killed early life off, and we wouldn't be here. So we're lucky to have this magnetic field, and the magnetic field is actually caused by that metallic core. All right. So you have that molten part of the core is what is causing the magnetic field. So it's called a magnetic dynamo effect. All right, so like we were saying, if you look down here, you can see that the south magnetic pole is aligned near our geographic north pole. Of course, that makes sense, given that remember that a south pole is going to be attracted to a north pole for a magnet. So if you have your bar magnets on your fridge, you can go take them off, a couple of them off the fridge, play with them and you know that, if you put two ends together that are both north or both south, you're going to feel that resistance. But if you turn one around so that you have a north pole and a south pole together, then they want to come together. So that's the idea here, is where your compass needle is going to point towards the south pole here of the south magnetic pole, which of course is near the geographic north pole. And notice they're not actually completely aligned, okay? All right. So, but it's very important that we have a magnetic field and also the source of the northern lights. Now, hopefully, someday you'll get to see this. Maybe some of you have already seen it. This is caused by atoms that are excited by the sun's particle and sort of driven down along the lines of the magnetic field. So let's look at a video for that. Okay, and this one we will do full screen. This is a really beautiful video of the aurora. And let's see if we can get my computer to cooperate. There we go. All right, cool, pretty nice. So I think it's worth watching that video all the way through.
Be honest.
Okay,
do you really want to
we
watch a
don't.
video that looks like this?
Let's go.
There's
All
a
right.
good reason.
Sorry about that. Really amazing sight. And again, these molecules are being excited by highly energetic sun particles that are coming off the sun. And the reason that you see all those lines and curves is because of the Earth's magnetic field. Now, when the molecules, once they get excited, if they de-excite, right, they release light, and that's where all that light's coming from. So I hope one day you get to see this. I haven't seen it yet, but hopefully you will. And maybe I will someday. All right, let's pause the video. Let me start my slideshow again so we can get to our question. And there we go. All right, pause the video, answer the question.